Welcome to Fresh Thinking by Snowden Optiro. I'm Susan Havlin, Managing Consultant for the Geology team in Australia at Snowden Optiro. Today we'll be delving into an application of machine learning for geological domaining in mineral resource estimations. Specifically, we'll examine a case study on using the K-means algorithm to identify ore and waste domains in a gold deposit. Joining me is Dr Gregory Zhang, a Senior Consultant at Snowden Optiro with over 14 years of experience in resource estimation and advanced geostatistical methods. He also develops various internal tools to customise the workflows as requested. Welcome, Greg.
Thank you, Susan. I'm pleased to be here to discuss the approach to addressing the geological domaining challenges.
So, Greg, let's start with the problem itself. Why was an alternative approach to traditional geological domaining needed for this project?
Well, geological domaining is crucial in mineral resource estimation as it determines the spatial boundaries between ore and waste. So traditionally, we rely on manual interpretation that combines geological logging and grade data, explicit or implicit modeling techniques. So in this particularly gold deposit, initial attempts to create geological domains using traditional methods led us to some highly irregular and discontinuous shapes that lacked geological coherence. So that posed risks to the accuracy of the resource model and downstream mining process. So given the volume and complexity of this dataset, over 30,000 samples containing both the numeric and categorical variables, we decided to test machine learning algorithms and to identify the patterns or relationships within the data that might not have been readily apparent to our human eyes.
That provides a really good background. Could you briefly explain what the K-means algorithm is and why it's suitable for this problem?
Certainly. K-means is an unsupervised machine learning algorithms that aim to partition a given dataset into K distinct clusters. So in the context of our geological domaining, we can consider the ore and the waste regions as different clusters. It is useful for dealing with the datasets where we want to group similar data points together. For our case, it can handle the numeric data related to the grade values and potentially helping declustering areas that might have similar characteristics in terms of mineralogy and, for example, alterations. So it is computationally efficient and provide a quick initial separation of the data into groups that might correspond to ore and waste domains.
Interesting. So what were the steps involved in applying K-means to this dataset?
So a couple steps. The first is data processing. So we dealt with missing values and normalized numeric features first. For categorical features, for example, lithology, alteration, or mineralogy, we need to convert them into numeric values in a meaningful way that we're going to use later. Then we're going to train the model and do some validation. So we first need to determine the appropriate number of clusters, which in our case is related to the number of distinct ore and waste regions we expect. Then we would run K-means algorithms on the dataset. And then last, the training only take a couple minutes. But since this method is sensitive to the initial cluster centroids and number of clusters, we need to test various combinations of the parameters and visualize the clusters in 3D to decide whether this result can give us some potential meaningful domains or not.
Wow, I mean, that sounds quite complex. So what were the key outcomes of this approach? Like, did it actually perform better than traditional methods?
So the K-means model were able to process the large datasets within a couple minutes. We were able to identify some patterns that were not as clear with traditional methods before. However, it also has its own limitation. While it gave a general separation of the data into clusters, the results are not as geologically coherent as we might have hoped in some areas. So we have to go further analysis and run a second K-means and combine it with other geological knowledge to refine this domain boundaries.
Wow, that's interesting. I'm glad to hear that you're using the geological knowledge as well, not just a machine learning approach.
Exactly.
So machine learning, like K-means, isn't without its limitations, right?
Absolutely.
You touched on them before.
Absolutely. The K-means algorithms have several challenges. For instance, the cluster initialization. So the results can be sensitive to the initial selection of the cluster centroids. So different initialization can lead to different final clusterings. And then how many clusters should we use? There's no straight way to exactly determine that the optimized or the best number of clusters. We have to rely on validation measures and domain knowledge, but it can still be a bit of trial and error process. And then while we can try to convert categorical data, it's just not as easy as the numeric data to be used in this kind of algorithm. So that means we might lose some valuable information from the transition from categorical data to the numeric data. So this is why machine learning algorithms like K-means should be seen as a complementary tool rather than a pure replacement for the traditional modeling methods. It can give us a starting point within a very, very short period of time, or it can just give us another different perspective when we do the geological modeling.
So just thinking, this sort of approach would be better for a large data set, right?
Yes.
And would this approach be, like, if you don't have a really strong understanding of your geological modelling, if you had a really strong, obviously, thoughts on your geological modelling, this would just be like a supplementary confirmation step, or would you just not do that?
It can still contribute to the project, but I mean, with the geological knowledge in our mind, it is always good to use that to fine-tune or just differentiate whether the machine learning algorithms giving us something sensible or not. And with larger data set or with smaller data set, and because it only takes a couple minutes to give us some clustering results, so I don't think there's any harm to give it a go. And if it makes sense to us, we can readily use that. If it doesn't make sense to us, we can fine-tune it, or we could just go with our traditional way. Either way, it can give us some quite good value.
So could your everyday resource geologist use this K-means?
Yes, we do. Certainly we do. With that algorithms put into a form of software or with some basic knowledge for the programming, you can use that, build that into our daily workflow. For example, I have that algorithm written in software where I use that nowadays for all the projects where I need to do the modeling.
That's interesting. Maybe I'll come and have a look.
Yeah.
So that's a valuable insight, Greg. Machine learning, when applied thoughtfully, clearly has the potential to enhance the accuracy and efficiency of geological domaining. Thank you for sharing your expertise on this case study.
You're welcome. Thank you, Susan.
If you're interested in exploring machine learning or other advanced techniques to solve resource estimation challenges, feel free to contact us at Snowden Optiro. And don't forget, if you like this podcast of Fresh Thinking, you can find more of our technical discussions on our website, Spotify, Apple Podcasts, and other platforms.